10 strange laws of physics. Stand under a clear night sky and look up. What you see appears calm, almost poetic. Stars scattered across darkness, planets moving silently, the universe unfolding in quiet order. For centuries, humanity believed that this order was simple, understandable, and predictable. Physics was seen as a tool to decode that order, to explain why things fall, why planets orbit, and why time moves forward in a straight line. But as our understanding deepened, something unexpected happened. The universe did not become simpler, it became stranger. Scientists began to uncover laws that did not align with human intuition. Time was not constant, space was not empty, matter was not solid, and perhaps most disturbingly, reality itself seemed to depend on whether it was being observed. This video is not just about scientific laws, it is about confronting the limits of human perception. What we call common sense is merely a survival mechanism shaped by everyday experience. It works well at human scale, but it fails when we explore extremes, whether incredible, small, or unimaginably large. This raises an important philosophical controversy. Is science meant to provide certainty, or does it reveal the depth of our ignorance? The answer, as modern physics suggests, is the latter. The more we discover, the more we realize how much remains unknown, and that realization is not a weakness, it is the foundation of curiosity. If reality itself behaves in ways we cannot intuitively grasp, then perhaps the true purpose of science is not to simplify the universe, but to prepare us to accept its complexity. The strange universe, at the scale of everyday life, the universe appears stable and predictable. You drop an object and it falls to the ground. You walk across a room and the floor feels solid beneath your feet. You glance at a clock and time seems to pass at a constant rate. These experiences create a powerful illusion that reality is fixed and reliable. However, this illusion begins to break the moment we step outside human scale. At cosmic levels, gravity does not simply pull objects together, it bends space itself, curving the very fabric of the universe. Massive objects like stars and black holes distort both space and time, creating environments where the rules we take for granted no longer apply. At the opposite extreme, in the quantum world, particles do not behave like solid objects at all. They act like waves, existing as probabilities rather than certainties, and their behavior changes when observed. This leads to one of the most profound insights in modern science. Reality is not absolute, it is dependent on scale and perspective. A phenomenon that appears stable at one level may behave unpredictably at another. Critics often argue that such ideas are too abstract or removed from practical life. However, these principles are not just theoretical, they have real world applications. Technologies like GPS rely on corrections for time dilation and modern electronics, and it depends upon quantum mechanics. This reveals a deeper truth. We are not experiencing reality as it truly is. but rather a simplified version shaped by our senses and cognitive limitations. The universe, in its true form, is far more complex, dynamic, and interconnected than our everyday experience suggests. Law number one, speed of light limit. One of the most fundamental rules of the universe is that nothing can travel faster than light. This speed, approximately 3 lakhs kilometers per second, is not just a measurement, it is a boundary that defines the structure of reality itself. Every interaction in the universe, every exchange of information, every cause and effect relationship is constrained by this limit. If an event occurs in one part of the universe, its influence cannot reach another location instantaneously. It must propagate at or below the speed of light. This ensures that cause always precedes effect, maintaining a consistent timeline across the cosmos. The idea of a universal speed limit has fascinated and frustrated scientists and storytellers alike. Science fiction frequently explores the possibility of faster than light travel, imagining warp drives or shortcuts through space. However, such concepts raise serious paradoxes. If something could travel faster than light, it could theoretically arrive before it was sent, creating a breakdown in causality. This is not just a technical issue, it challenges the logical structure of reality itself. While theoretical models like wormholes exist, there is no experimental evidence to support faster than light travel as a practical reality. The deeper implication of this law is that the universe is not just governed by speed, it is governed by constraints designed to preserve order. These constraints may limit us, but they also make the universe coherent and predictable. Law number two, time slows down at high speed. Time feels like one of the most constant aspects of existence. It moves forward second by second, seemingly unaffected by anything we do. However, Einstein's theory of relativity reveals that this perception is incomplete. Time is not absolute, it is relative to motion and gravity. When an object moves at a speed close to that of light, time for that object slows down relative to a stationary observer. This phenomenon, known as time dilation, has been experimentally verified using highly precise atomic clocks. Even astronauts aboard fast-moving spacecraft experiences time slightly differently from those on the Earth. This discovery leads to fascinating and sometimes unsettling questions. If time can slow down, does that mean time travel is possible? The answer is both yes and no. Forward time travel is not just possible, it is already happening, albeit on a very small scale. However, traveling backward in time remains speculative and unsupported by current physics. The deeper implication is that time is not a universal flow. shared equally by all observers. Instead, it is a personal experience shaped by movement and gravitational forces. This challenges one of the most deeply ingrained assumptions about reality, that time is the same for everyone. In truth, each observer experiences their own version of time, making reality far more subjective than it appears. Quantum superposition. At the quantum level, reality behaves in ways that defy classical logic. One of the most striking examples is the principle of superposition, which states that a particle can exist in multiple states simultaneously, unlike objects in the everyday world which occupy a single position at a given time. Quantum particles exist as a range of probabilities. An electron, for instance, does not orbit the nucleus of an atom in a fixed path. Instead, it exists as a cloud of potential locations where it might be found. Only when a measurement is made does the particle collapse into a specific state. This idea challenges our understanding of existence itself. How can something be in multiple states at once? The answer lies in the wave-like nature of quantum particles. They are not solid objects but probability waves that spread across space. This leads to a deeper philosophical controversy. Does reality exist in a definite form before it is observed? Different interpretations of quantum mechanics offer different answers, but the experimental results are clear. Superposition is real. The implication is profound. Reality is not fixed until it is measured. This suggests that certainty is not a fundamental property of the universe. Instead, it emerges from interaction and observation. The observer effect, one of the most counterintuitive discoveries in physics, is that the act of observation can change the behavior of a system. In quantum experiments, particles behave differently depending on whether they are being measured. For example, in the famous double slit experiment, particles create an interference pattern when unobserved, behaving like waves. However, when observed, they behave like particles, producing a completely different pattern. This phenomenon is known as the observer effect. At first glance, this raises a controversial question. Does consciousness influence reality? While this idea is often misunderstood, the scientific explanation is more precise. Observation in physics does not necessarily mean human awareness. It refers to any interaction that extracts information from a system. Measurement involves interaction, and that interaction alters the system being measured. Nevertheless, the philosophical implications are significant. It suggests that there may be no completely objective reality independent of observation. Instead, reality is shaped, at least in part, by the interactions that reveal it. This challenges the traditional view of a detached observer studying an independent universe. Instead, it places the observer within the system, making observation an active participant in the unfolding of reality. Empty space is not empty. When we imagine empty space, we often think of complete nothingness, a silent, inactive void where absolutely nothing exists. This idea feels intuitive because our everyday experience associates emptiness with absence. However, modern physics reveals something far more fascinating. What we call empty space is not empty at all. Instead, it is filled with invisible energy fields that constantly fluctuate. In these fluctuations, particles can spontaneously appear and disappear within incredibly short periods of time. These are known as virtual particles, and although they exist only briefly, their presence has measurable effects on the universe. This discovery challenges one of the most fundamental assumptions about reality, that something cannot come from nothing. Critics often question this idea, asking how particles can emerge without a source. The answer lies in the principles of quantum mechanics, particularly the uncertainty principle, which allows temporary violations of energy conservation within extremely small time intervals. While this may seem like a loophole in the laws of physics, it is in fact a well-tested phenomenon. The deeper implication is profound. The universe is not built on static emptiness but on continuous activity. Even in places where we perceive nothing, this suggests that nothingness is not the absence of existence, but a hidden layer of dynamic potential. It transforms our understanding of space from a passive background into an active participant in the structure of reality. Quantum entanglement. Imagine two particles created together in such a way that they become deeply connected. No matter how far apart they move, their states remain linked. If you measure one particle, the other instantly reflects that change. Even if it is located on the opposite side of the universe, this phenomenon known as quantum entanglement is one of the most mysterious aspects of modern physics. It appears to defy the very concept of distance, suggesting that information or influence can travel instantaneously. This idea troubled even Einstein, who famously referred to it as spooky action at a distance. The controversy arises from the apparent violation of the speed of light limit. If the effect is instantaneous, does it mean something is traveling faster than light? The answer, according to current understanding, is no. Entanglement does not allow for the transfer of usable information faster than light. so it does not break the fundamental rules of causality. However, it does reveal that the universe operates in ways that are not fully captured by classical concepts of space and separation. The deeper meaning of entanglement is philosophical as much as it is scientific. It suggests that separation may be an illusion at a fundamental level. What appears to be distinct and independent objects may in reality be part of a single interconnected system. This challenges the idea of individuality and independence in the physical world, hinting that the universe is more like a unified network than a collection of separate parts. Matter and energy are equivalent. One of the most famous equations in physics, introduced by Einstein, reveals a simple yet revolutionary idea: matter and energy are interchangeable. This means that the physical objects we see, our bodies, the earth, the stars, are all forms of energy condensed into a stable structure. Under the right conditions, matter can be converted into energy, and energy can be transformed into matter. This principle lies at the heart of nuclear reactions, both in the destructive power of atomic weapons and the life sustaining processes within stars. At first glance, this concept may seem abstract, but its implications are immense. It tells us that the distinction between matter and energy is not fundamental. They are different expressions of the same underlying reality. This raises an important ethical controversy. The same scientific principle that powers the sun and enables life on Earth has also been used to create some of the most destructive weapons in human history. This duality highlights a critical truth. Science itself is neutral, it provides knowledge, but it is human intention that determines how that knowledge is applied. On a deeper level, this law reshapes our understanding of existence. If everything is fundamentally energy, then the solid world we perceive is not as fixed as it appears. It is a dynamic, ever changing system where form and substance are constantly interacting. This perspective invites us to see the universe not as a collection of rigid objects, but as a flowing continuum of energy in motion. Black holes warp reality. Black holes are among the most extreme and fascinating objects in the universe. Formed from the remnants of massive stars, they possess gravitational forces so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. But black holes are not just powerful gravitational traps. They are regions where the very fabric of space and time is dramatically distorted. Never near a black hole, time slows down relative to distant observers. If you were to approach one, an outside observer would see your movements gradually slow until they appear to freeze at the event horizon. Meanwhile, from your perspective, time would continue normally, but the outside universe would appear to speed up. This creates a profound distortion of reality where different observers experience entirely different versions of time. The greatest controversy surrounding black holes is what happens beyond the event horizon. Do the laws of physics continue to apply or do they break down completely? Current theories suggest that our existing models are insufficient to fully describe these conditions. Black holes represent a boundary of knowledge, a place where general relativity and quantum mechanics must somehow be unified, but where a complete theory has yet to be discovered. Philosophically, black holes symbolize the limits of human understanding. They remind us that no matter how much we learn, there will be always be regions of reality that remain beyond our comprehension. Instead of being a failure of science, this is a powerful motivation for further exploration. The expanding universe. For much of history, it was assumed that the universe was static and unchanging. However, observations in the 20th century revealed a startling galaxies are moving away from each other and the universe itself is expanding. This expansion is not like objects moving through space. Rather, space itself is stretching, increasing the distance between galaxies over time. This discovery leads to one of the biggest questions in modern physics: what is driving this expansion? The leading explanation is a mysterious force known as dark energy, which appears to push space outward at an accelerating rate. However, the true nature of dark energy remains unknown, making it one of the greatest unsolved mysteries in the science. The controversy here lies in the limits of our understanding. If most of the universe behavior is driven by something we cannot directly observe or fully explain, how complete is our current model of physics? The answer is clear: it is incomplete. Yet, this incompleteness is not a weakness, it is an opportunity. It shows that the universe is still full of secrets waiting to be discovered. On a deeper level, the expansion of the universe changes our perception of existence. It suggests that the cosmos is not static but evolving, constantly growing and transforming. This dynamic nature reflects a broader truth: change is not an exception in the universe, it is the rule. The invisible universe. One of the most humbling discoveries in modern physics is that everything we can see, stars, planets, galaxies, and even ourselves, accounts for only about 5% of the universe. The remaining 95% is composed of dark matter and dark energy, both of which are invisible and not yet fully understood. Dark matter does not emit or absorb light, but its gravitational effects reveal its presence. Dark energy, on the other hand, appears to drive the expansion of the universe, yet its nature remains one of the greatest mysteries in the science. This realization challenges the assumption that we understand the universe simply because we can observe. In reality, most of existence lies beyond our direct perception. This raises a profound question: how much of reality are we truly aware of? The controversy here is not just scientific but philosophical. If the majority of the universe is invisible and unknown, can we ever claim to have a complete understanding of it? The answer for now is no, but this does not diminish the value of scientific inquiry. Instead, it highlights its importance. The invisible universe reminds us that the knowledge is always incomplete and that discovery is an ongoing process. It encourages humility and curiosity, two qualities that are essential for progress. As we reach the end of this journey, one truth becomes clear: the universe is far more complex, mysterious, and beautiful than we ever imagined. The laws we have explored do not just describe physical phenomena, they challenge our perception of reality itself. They reveal a world where certainty is replaced by probability, where observation influences outcomes, and where most of existence remains unseen. This leads to a final powerful insight. The goal of science is not to eliminate mystery, but to deepen it. Every discovery opens new questions, and every answer leads to further exploration. This is not a limitation, it is the essence of human curiosity. It is what drives innovation, fuels discovery, and pushes the boundaries of knowledge. The ultimate controversy is whether we will ever fully understand the universe. Perhaps we will not, but that is not a reason to stop searching. On the contrary, it is a reason to continue, because in the pursuit of understanding, we do not just learn about the universe, we learn about ourselves. The universe is not something to be fully solved, it is something to be endlessly explored. And that exploration is what makes us human. Thank you. Have a nice day.